Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll help get you started with Class 10, the analysis of a two-way factor design. We will look again at the Kangaroo dataset that we saw in the previous assignment. So here we are, Class 10, and we've got a markdown file to download as well as a data file, though I believe that data file is the same as from last class. So if you've already downloaded that, you don't need to download it again. You'll know for sure, at least on Windows, because it will try to append a %1 to the file name. So we don't need to download that. Let's open it up over in RStudio, knit it, and we'll get started. Set the working directory to the source file location and knit. Oh, that knit very quickly. All right, let's open this in browser so we can zoom in. So similar to class 9, we're going to look at the same data set but a different variable. So we're still looking at skull measurements, and this time we're looking at mandible length. So we're going to look again at sex and species. Those are the star, and here the star for mandible length. We read the data set in, but this time we are selecting the mandible length variable, and it turns out that there are some missing values. So when we look at calculating how many missing values there are 12. Okay, I discussed this code on the last video. This time looks like oh no, that's just the beginning of the data set. Great. All right, so now if I just scroll down, you can see I haven't given you very much. So the assignment is very much the same as assignment 9, and so this is your opportunity to do a little bit of copy and paste and to get everything in here that you need for this assignment. So first thing we're going to do is make sure that we can plot the data. Then we will assess whether there's interactions in those plots. We'll fit the two-way interaction model, check those model assumptions. We'll reduce. Oh yeah, and then we'll assess. We'll do a hypothesis test for whether the interaction and main effects are significant. If the interaction is significant, then we're going to keep that interaction model. Otherwise, if the interaction is not significant, we can drop it and then see whether the main effects are still important and reduce the model as required, and then summarize the differences between sex, species, or combinations of them. All right, so I'm going to go over to RStudio, and let me open up the assignment 9, the markdown file. And I just went to the very top, and I'm going to page down now to where the code starts for those summaries. Okay, so this in assignment 9. This is interpreting the plots. Okay, so this is the same area. Now, what I find to be the easiest when we're doing something big like this, where we've got lots of pieces of code to move over, is almost everything is identical, except instead of crest width, CW, we're looking at crest length, CL. So what I would do is copy all the code over that we think we need, and then do a find and replace, and be very careful and try. I think CW is going to be fairly unique. I can't think of words that have CW next to each other in Word, so probably we can just replace all the CWs and have that work. But we'll just replace CW with crest length over on the other assignment. So let's copy all this code. These are the plots. And now on the assignment 10, I'm going to scroll down to the plots. Okay, so here I'll add them here. Sorry, I realized that might have been a little bit fast. I just put my cursor under the section for interpret plots, and I pasted that plotting code there. Okay, so now I'm going to scroll down, and okay, so the interaction is just about interpreting the plot, and then fit the two-way interaction model. So this is where I'm expecting the next piece of code to go. So now we'll go over to class 9, scroll down, and finding, here it is, the model for that. So I'll copy that code, go over to assignment 10, and paste it. And I'm not worrying about the CWs yet, because I'm going to replace those a little bit later. Okay, so after that code is there, check model assumptions. Okay, so class 9, go get the code for that. Here we go. Copy that over to assignment 10. You get the idea. Okay, scroll down to the ANOVA table. Copy that. Assignment 10. Scroll down to the ANOVA table. Paste it. Okay, reduce to final model and test assumptions. All right, let's just keep going. Might as well just put all the code in there, and we can delete stuff that we don't need later on if that's the case. So I'm going to copy over the code that has just the main effects, and maybe we need it, maybe we don't. Okay, and then what else do we have? We have the EM means code. So this is pretty good, but there's some other code that I prepare this part of the assignment with. So I'm actually not going, you know what, let me copy it over. Let's just assume that everything's going to be the same for a moment. And we can always delete it later if we don't need it. Okay, I'll just sort of dump it here at the very bottom. Okay, so now we've got everything in there. We don't need assignment 9 anymore. So you could leave it open, but I'm just going to close it so it's not distracting. And now I'm going to replace, I'm going to do, oh, I'm going a little too fast, sorry. Control F, we'll do a find. And now put in CW for crest width, and I'm going to replace that with CL for crest length. And you know what, I'm going to scroll up and just double check. Oh, I'm glad I'm glad I did, because it's actually ML, mandible length. Okay. So that is the replacement that I want to make. Let's find the next one. Okay, so we are starting at the very top, which is good. We don't want to change it in the code book, so we're going to do next. Now here's where we're starting to have code and we're doing calculations. We want all these to be mandible lengths. I apologize for all the times I said crest length. Okay, so mandible length. So now I'm going to do some replacements. And every time I click, okay, I'm making sure that the highlighted text is one that I want to change. And it looks like all the ones, so the only one not to change is the one in the code book. So we'll skip that one, and we've done, okay, if I click next over and over again, it's just bringing me back to the same one. So that's the last one. We're all done. Now, if I knit it, will all the code run? I think so. Let's try. Okay, that's a very quick way to assess whether we got everything right. And we can use this to start looking through and assessing the plots and so on within the browser, which I think is an easier place to do it for myself in the video. When I work at home, I almost never do these types of things in the HTML file. I always look right in RStudio, but for demonstration purposes, it's pretty good in here. All right, so we've got these means for each mandible length. The means for mandible length by different groups. So 1250 roughly is the overall grand mean. It looks like males are bigger in this case. So females had larger crest widths, but males have longer mandible lengths. Looks like there may be differences by species. This one in the middle seems lower than the other two. And there may be interactions. It looks pretty hard to interpret right here in this table, but fortunately we just made this plot. And all right. So one thing here that's not working for me is 0 is included in the range, and I think that's creating too much blank space. Let's scroll up at the code and see. Looks like I made this horizontal line at 0. Now typically I think that it's useful, it can be useful to have 0 in a plot when there's a measurement like this. But since it creates so much of a gap and it's harder to see the differences, I'm going to go over to RStudio and remove that horizontal line. So I'm just paging down until I find the code. And I like the line of code, so I'm just going to comment it to leave it in there. I'm going to take it out of both plots and knit it again. Okay, so this plot now is taking up much more of the vertical space, much easier to see the differences. So in terms of means right off, it looks like there's a big sex difference in the MFF group between males and females, but it's sort of horizontal for the red and a little less so for the green. So not big sex differences between the sexes for the red and green species. If we look over here, it's another way of seeing the same thing. Now species is on the horizontal axis, and we have sex as the colors. We see males and females very similar for the MG species, a little bit different for MFM, but then big differences for this species. So does this suggest that there's an interaction between sex and species? Our guide here is whether or not these lines are parallel, and looks like there's a big difference in angle or a big angular difference between these two lines. So for sure I think there's going to be an interaction here. In fact, when you look at the distributions of the data, you can see how much the males and the females overlap, right? They're almost the same median, and over here they're a huge difference. About 50% of the data overlap, but the males have entirely 50% greater than the maximum for the females, and the females have a 50% less than the minimum of the males. So big difference there for this last species. So I'm predicting that there's going to be an interaction. Let's go get the question from the heading. Interpret the plots of the data, the distributional centers, and the shapes. So shapes, what do you think? Do we have symmetric distributions, skewed right or left? I think these are largely symmetric distributions. We have a little bit of skewness, I think. Not very much. So this, yeah, I would say not very much skewness. So I think our model assumptions are probably going to be met also. So I would say, you know, the distributions look roughly symmetric, roughly equal variance over all the 6 combinations of groups, and likely an interaction, especially for that the difference in sex for the MFF species is much larger than the difference between the sexes in the other 2 species. That's my main takeaway here. All right, so that answers this question. All right, let's fit the 2A interaction model. Now recall that this star expands. You know, I should have rewritten this in our last video just to demonstrate, but the same, this star expands out to be that equation there. We have sex plus species plus the interaction sex colon species. Okay. Where, you know, in mathematical terms, this colon now is actually a multiplication sign. It's treated differently within an R formula environment because of factors. Sex and species aren't actually individual effects, but they represent, you know, 2 and 3 categories each. And so this colon is doing a lot of work to keep track of which level is the baseline level and which combinations of factors need to be included in the model for those effects. Okay, let's keep going. Oh yeah, we're going to look over here. So check model assumptions. So we've got ML now is the object, the linear model object name, and we'll plot those diagnostic plots. Oh man, that's pretty good. There's a little bit of weirdness happening in this left tail. It's like we sort of starting to have sort of residuals that are not as extreme as you'd expect, and then there's a jump where we have a few that are a little bit more extreme. But gosh, this is anything that makes me say gosh is a pretty good sign. So this is these residuals all look quite good. In terms of Cook's distances, same thing. Observation 6 is a little more influential than a couple others, but not by very much. I don't really see any real issues here. You can't really interpret the leverages because we just have factors. In terms of equal variance over time, these all look, or over the fitted values, these all look pretty good. The spreads here are about the same. We sort of have these 3 outliers for these females, but I don't know, sort of min and max are about the same. The spread of the inner box plot is a bit different. So, right, what does this inner box represent? How much of the data? So it's from, right, the lower stem down here is the minimum. So we have the Q1, median in the middle, Q3, and the maximum. So between Q1 and Q3, between those 2 quarter points, we have 50% of the data. So it seems like the middle 50% of the male data is a little bit wider than middle 50 of the female. These differences I think of as not being very big. Over the 3 species, these are pretty similar as well. There's not really any evidence for variances not being constant. Excuse me. Okay, so now we're getting some structure here when you compare the residuals versus the index. And I am quite sure that that's because this data is probably sorted in the data set. I haven't looked at this yet, but what if we open up the data file, the Kangaroo CSV. Now this is probably impossible to read. But you can already tell that it's sorted. Look at the sex and species columns, all the 1s and all the 0s. So it's at least sorted by the sex and species groups. And if I scroll down, sex went from 1 to 2, and now we've got all of the 0 species, and then that changes to 1, 1. So because it's sorted by sex and species, we're getting some structure here. So this is not an interpretable plot because it's sorted by the observations and not by the measurement process. All right, Box-Cox is not suggesting a different transformation. We have interactions in the model, so we're not going to interpret the collinearity. Furthermore, these are factor variables, so collinearity doesn't really even make sense. And all the added variable plots. It seems that observation 6 is sort of an outlier always. It's one that's where the mandible length is too small relative to the rest of the distribution. So that's the reason why it's influential. Do we think, so another piece of information the added variable plot gives is is this outlier here somehow changing the relationship that you see, this slope? Is it having an effect on that slope? And I would say no. There's a whole bunch of points up here. That one observation is not, say, pulling this line down in order to remove a steeper slope that would otherwise be there. I just don't see any of these outlying observations as being very influential. So I feel pretty good about everything that I'm seeing there. All right, so that's everything to talk about the solutions there. Let's look at our analysis variance table. We want to see whether there's an interaction, and gosh, I said it again, there is. So there is evidence that there's an interaction, and we're not surprised because if I page up, we saw this huge difference between the sexes for this one species that was not there for the other species. Therefore, the difference in sexes depends on which species you're in. Therefore, there's an interaction. I'll page back down. All right, so now reduced to final model, we're done. We don't need to do this part because the final model is the full model because the interaction is significant. So let's go back over to RStudio and all right, so here's the reduced to full model code, and I will just say I'm going to remove all the code because we're going to use the full model. So, full model is the final model because the interaction is significant and the model assumptions are met. All right. So we're happy with the reduced model. So all this stuff is going to go away. We're skip. That's for the main effects model. Okay, summarize the differences. That's where we're at. So now we've got an interaction. Therefore, these two contrast lines are the ones that we want. We want to know, are there differences between the sexes for each species, by each species? So, how is the male and female mandible length different for species 1, species 2, species 3? And similarly, how are the species different for each sex? How do they differ for females and how do they differ for males? Those two sets of contrasts are exactly what is shown basically in this plot here, right? So this plot on the left, where we're comparing males versus females. So this blue line says that there's a big difference for, well, I guess you can look at either of these plots in the same way. Which way do we want to look at it? Let me go the other way. Let's look at this species here. So for each species, what is the difference in sex? So that's just this vertical distance. Okay, so there's a big difference here, small difference, almost no difference. You go looking at the other way, within males, what are the differences between species? It looks like MFF is bigger than the other two. And for females, looks like they're maybe all about the same. It's possible that the red is larger than the blue, but maybe all about the same. So from this plot, we've developed some intuition about what we expect to see. And if we see something that surprises us, well, now that we've got intuition, we'll know whether or not we should be surprised, right? It won't just blindly follow the result. So I just pressed end to jump all the way down. So we don't want these first two. In my opinion, main effects don't really make much sense to interpret if there's an interaction in the model, because differences between sex depend on which species you're in. So we're going to delete these two for the main effects, and we're going to use these two for the interactions. All right, so I'm going to go over to RStudio, and I sort of like some of the code that I copied over here from the previous assignment over here, but I'm gonna make this work with the test that we actually want. So the main thing that we want is we want these lines of code here to look at differences in sex by species and differences in species by sex. So those are the ones I'm going to copy. I'm going to come down here to what we did last time, and I'm going to make a couple modifications. I'm going to paste both those lines in here. Actually, it's a little bit hard to know how to, okay, hang in there with me. All right, so I've got to use my interaction model. There's my interaction object. You see that it popped up. It knows that that variable is inside of our, it's inside of our code anyway. Okay, so that's the linear model object I want, but I'm going to delete all this stuff so that I have the sex and species here. Okay, and I'm going to move the species one down to the species section. So now I'm going to go down and paste it here and put in my interaction XS, and then make that species by sex. Okay, I think that is pretty much everything that I need. Now, these aren't going to apply anymore, right? We're going to have to redo this. But let's knit this and look at those last pairwise comparison results. So I'll refresh this page, scroll down. Let's see, do I have too much junk here? I can probably remove some of this code that is commented. Okay, so here's sex. So I've got my interaction here, linear model object, and it's got the for the mandible length. That's correct. I'm looking at sex by species. And so the first set of output is just the means and the confidence intervals. So for the first species, MG, the male has 1266 and the female is 1249, and there's a confidence interval for each one. Okay, this is not the output that we're interested in. I just wanted to interpret it. The second one is the second species, and then the third species. Now let's go down and look at the pairs, and this is doing now the comparisons. We have for the first species, MG, males minus females. So males are 17 tenths of a millimeter larger than the females, and that is not significant. For the second species, the contrast is 48. The difference is 48 with a p-value of 0.23, not significant. But for the last one, MFF, the contrast between male and female is 183, which is significant, with a t-statistic of 4. Basically 4 standard errors away from 0, so that's pretty large effect. That is what we see. Oh, let me scroll down a little bit. Okay, so we've got, I can see now I need to make this a little taller so we can read these species boxes. But we see that there's no difference for the first one, no difference for the second one. I'm drawing vertical lines and seeing whether the two red lines can overlap that vertical line. And if those red lines overlap, then there's no difference. Third species, big difference. Okay, so this plot is basically, if I page up or scroll up really quickly, it's basically this plot on its side, where this was at the top, middle, and bottom. Yeah, top, middle, and bottom. Okay, so I will modify the side. In fact, let's go do that since we just thought about it. So these heights, the height of 2 worked well when they were just main effects. Maybe we'll make it twice as tall, 4 inches. Okay, I'll knit that. We'll go over and keep reviewing the results. Now for species, same thing. We're looking at the species differences by sex. So now we've got The means and confidence intervals for males, there are the means for males and their confidence intervals. And then over here, we've got the pairs. So these are the contrasts. So now, are there differences between species for males? Not between these first two. P-value is very large. For these second ones, not really. And for these third ones, 0.04. Now it is adjusted for, I think, within each of these two. So within these three tests, the Tukey method is applied, and within these three tests, the Tukey is applied. It's not actually applied over all six. So, so probably this 0.04 becomes not significant if you apply it over all six. But let's just take these p-values as they are, and not worry too much about that. So it appears then for males, between the second and the third species, that there are differences, but no differences for females. All these p-values are large. If we look at a plot for this, for males, you can see, yeah, this MFF is the top one. That one is different from the second one, MFM, but not different from the third. And I'm sort of counting them. I sort of enumerated those backwards. In these plots, the first one's at the bottom and it goes upwards, but you get the point. So MFF and MFM are different for males, but for females, not really a difference. Now you can see that the means, the black dots, are, show evidence of a little bit of some differences, but they're not statistically significant. All right. I feel pretty good about that. Oh yeah, let's refresh this. That will make our plots bigger. Okay, that works better for these species plots. And we might as well keep the sex plot on the same scale, the same spacing, though it looked fine when it was short. I would interpret each of those. Let's see. We could go through the exercise of making these plots for each group, but I think we can probably go ahead and skip that for this assignment. So I would, in this solution area, after those plots, I would discuss the differences. So as we said before, yeah, for this species, is there a difference in sex? No. For this species, is there a difference in sex? No. For this species, there is a difference in sex where males are estimated to be 183 larger than the females. That would be my discussion, and you could do a similar interpretation of differences between species within sex. All right, summarize the results in a few sentences. Okay, so I would sort of go up to the top and scroll down and think about writing a few sentences that encapsulate the data, what you saw in the plots, what model you fit, whether the model assumptions fit or were satisfied, and then the pairwise comparisons. Okay, so I'm going to scroll to the top and I'll just sort of dictate to myself a few sentences. So if this was me, if I was writing this assignment myself, as I scroll down I would type a few sentence fragments as I go along, and then I would summarize that. Okay, so we looked at something like, so I'll start dictating now. We looked at kangaroo skull measurements of mandible length for sex and 3 species of kangaroo. Let's see. When plotting the data, we observed that within the MG species, the sexes had similar sizes. There were a small difference in sizes for MFM, but a large difference for MFF, where the male sex was consistently larger than the females. Okay, so that's a first summary of the data. We fit a two-way ANOVA model with interaction between sex and species, and all the model assumptions were met. Residuals were normal, no strongly influential points, and equal variance. That's probably everything you need to say for model assumptions. The interaction for the model was significant. So we, so the full model is our final model. We summarize so we look at differences between sexes for each species and for species for each sex. We observed that there are differences for species MFF between sexes, where the males are larger than the females. However, there were not statistical differences for the other two species. Additionally, for males, there were mean differences in mandible length between the MFF and MFM species, where the MFF species was 100 tenths of a millimeter larger than the MFF, or than the MFM species. However, for females, there were no statistical differences. I think if you write up something like that, you've captured all the elements of the analysis, and if you were to write that in a sentence in a research paper, you've given, I think, enough detail for anyone to reproduce your analysis, and that you've justified all the decisions you've made because model assumptions were met and things like that. So I think that's hope this was helpful for you for this assignment, and we'll see you in the next one.